Imagine the universe as a tiny, hot speck, smaller than a grain of sand, holding the entire cosmic library within it. This isn't the start of a sci-fi tale. It's the real deal, the birth of our universe. In the blink of an eye, this singularity exploded, not just in a boom, but in an unimaginable cosmic dance that stretched, cooled, and shaped everything we see today. We're talking about the Big Bang, and it's not just a theory. It's the ultimate origin story, and it's way more mind-blowing than any superhero saga. Stick around, because we're about to zoom through 13.8 billion years of cosmic history, from that initial singularity to the rapid expansion known as cosmic inflation. This is the story of how we got here, and trust me, it's a wild ride. The cosmic egg. What is a singularity? At the heart of the Big Bang theory lies a mind-bending concept. The singularity, often metaphorically referred to as the cosmic egg. This isn't a literal egg, of course, but a term that captures the idea of a single, infinitely dense point from which our universe sprang. Think of it as the ultimate cosmic seed, packed with all the matter and energy that would eventually unfold into the vast, complex cosmos we observe today. The singularity is a point where the laws of physics, as we know them, break down. It's a place of infinite density and zero volume, a mathematical absurdity that challenges our understanding of reality. This isn't just a theoretical quirk, it's a fundamental aspect of our universe's origin story. To grasp the singularity, consider a black hole, but crank up the intensity to 11. At the center of a black hole lies a singularity, a point where matter is crushed to infinite density. Now, imagine that, but on a cosmic scale. The Big Bang singularity is like the mother of all black hole singularities, the ultimate cosmic crunch. It's a place where space and time themselves begin, a starting point for everything that followed. The term cosmic egg is apt because, like an egg, it contains within it the potential for everything that will come after. It's a metaphor that captures the idea of a simple, compact beginning that holds the promise of complexity and diversity. The singularity is a boundary, a point where our current understanding of physics reaches its limit. It's like trying to describe a color to someone who's never seen light. The concepts don't yet exist. This is why the singularity is so fascinating and frustrating. It's a puzzle piece that doesn't quite fit into our current puzzle. Scientists are still working to understand what, if anything, came before the singularity. Was it a quantum fluctuation in a pre-existing universe? A collision of higher dimensional objects? Or something else entirely? The answers to these questions could rewrite our understanding of reality. Until then, the singularity remains a cosmic enigma, a reminder of how much we still have to learn. A universe in a nutshell, the initial conditions. Picture the universe as an enormous, ever-expanding balloon. Before it was a balloon, it was a tiny, dense point, a singularity, where the laws of physics as we know them ceased to make sense. This singularity wasn't a physical object, but a point of infinite density and temperature, a cosmic seed from which everything sprang. It's like trying to imagine a single drop of water containing an entire ocean, or a single spark capable of igniting a wildfire that never stops growing. In this primordial state, the universe was a hot, dense soup of particles and energy, a chaotic mix where quarks, electrons, and other fundamental particles danced wildly. It's akin to a pot of water boiling furiously, with particles bouncing around at speeds approaching the speed of light. This primordial soup was so hot and dense that particles couldn't combine to form atoms. Instead, they existed in a state of constant flux, a cosmic stew where everything was energy and potential. The initial conditions of the universe were set by this extreme environment. The universe was not only incredibly hot and dense, but also remarkably uniform. This uniformity is a bit like a perfectly smooth canvas, ready for the brushstrokes of cosmic evolution. Tiny quantum fluctuations, like the faintest ripples on that canvas, would later grow to become the large-scale structures we see today: galaxies, clusters, and superclusters. These fluctuations were the seeds of cosmic structure, the tiny imperfections that would eventually lead to the complex tapestry of the universe we observe. The universe's initial conditions also included a rapid expansion phase known as cosmic inflation. Imagine a tiny speck of dough that suddenly expands into a vast loaf of bread. In a fraction of a second, the universe expanded exponentially, smoothing out any irregularities and setting the stage for the universe we see today. This rapid expansion was driven by a hypothetical field called the inflaton field, which filled the universe with a repulsive gravitational force. The inflaton field's energy density decreased as the universe expanded, eventually giving way to the more familiar forces and particles we know. This phase of rapid expansion explains why the universe appears so uniform and flat on the largest scales. The first picosecond, a quantum leap. In the beginning, there was a singularity, a point of infinite density and temperature, where the laws of physics as we know them ceased to exist. Then, in a cosmic blink of an eye, the universe inflated faster than the speed of light. This initial burst, known as cosmic inflation, set the stage for everything that followed. But let's rewind even further to the first picosecond, a trillionth of a second after the Big Bang. This fleeting moment was a quantum leap, a transition from the quantum foam of the singularity to the classical universe we're familiar with. Picture the universe as a tiny, seething bubble of pure energy, where particles and forces were indistinct. In this chaotic soup, quantum fluctuations were the norm. These fluctuations, tiny ripples in the fabric of space-time, were the seeds that would eventually grow into galaxies, stars, and planets. During the first picosecond, these fluctuations were amplified by the rapid expansion of the universe, a process known as quantum inflation. It's like a tiny pebble dropped into a pond, creating ripples that grow larger and larger. As the universe expanded, it cooled. This cooling allowed the fundamental forces of nature to separate from each other. First, gravity broke away from the other forces, followed by the strong nuclear force. Then, the weak nuclear force and electromagnetism split, leaving us with the four fundamental forces we know today. This process, known as symmetry breaking, is akin to a phase transition, like water turning into ice. It's a sudden change in state, triggered by a change in conditions. In this first picosecond, the universe was a hot, dense plasma, a soup of quarks, electrons, and their antiparticles. As the universe continued to expand and cool, these particles began to combine, forming protons and neutrons. This process, known as nucleosynthesis, laid the groundwork for the atoms that make up everything we see today. It's like a cosmic recipe, where the right ingredients and conditions come together to create something new and complex. And all of this happened in the blink of an eye, a quantum leap from singularity to the universe we know. Inflation theory, the universe's growth spurt. Picture the universe as a tiny, dense, smaller than a grain of sand. This is the singularity, the starting point of everything. In a fraction of a second, it exploded, and the universe began to expand. But this wasn't a steady growth. It was more like a balloon being inflated at an ever-increasing rate. This rapid expansion is what scientists call cosmic inflation. Inflation theory suggests that the universe underwent an exponential growth spurt in its first tiny fraction of a second. It's like a cosmic growth spurt, where the universe grew from something unimaginably small to something incredibly vast in the blink of an eye. This rapid expansion smoothed out any irregularities and made the universe uniform. Think of it like a baker kneading dough, ironing out any lumps and creating a smooth, even surface. The theory also explains why the universe looks the same in all directions. It's like being in a vast, empty room with mirrors on every wall. No matter where you look, you see the same reflection. This uniformity is a key prediction of inflation theory. It's also backed up by observations of the cosmic microwave background radiation, the afterglow of the Big Bang. This radiation is incredibly uniform, just like inflation theory predicts. But inflation didn't last forever. After that initial burst of growth, the universe settled into a more sedate pace of expansion. It's like a teenager who grows several inches in a year and then slows down to a more normal growth rate. This slower expansion continues to this day, with galaxies moving away from each other as the universe grows larger. Yet, the echoes of that initial growth spurt are still visible in the structure and uniformity of the cosmos. It's a reminder of the universe's humble beginnings and the incredible journey it has undertaken since. The cosmic microwave background, echoes of the Big Bang. Picture the universe as a vast symphony and the cosmic microwave background, CMB, is its first, faint melody. This ancient light, a whisper from the universe's infancy, is a snapshot of the cosmos when it was just 380 years old. It's like finding a baby picture of the universe, a time when it was a mere toddler compared to its current age of about 13.8 billion years. The CMB is the oldest light we can see, a relic from an era when the universe was hot, dense, and opaque, like a thick fog. As the universe expanded and cooled, it became transparent, allowing this light to travel freely, carrying with it a wealth of information about the early universe. Think of the CMB as the universe's fingerprint, a unique pattern of temperature fluctuations that tells a story of cosmic inflation, the rapid expansion that occurred in the universe's first tiny fraction of a second. These fluctuations, tiny variations in temperature of just a few parts in 100, are like the crinkles on a baby's skin, subtle but revealing. They are the seeds from which galaxies and stars would eventually grow. The CMB is also remarkably uniform, with a temperature of about 2.7 Kelvin, a testament to the universe's remarkable homogeneity on large scales. This uniformity is a key prediction of the Big Bang theory, a theory that has been remarkably successful in explaining the universe we observe. The CMB is not just a historical artifact. It's a treasure trove of information about the universe's composition, shape, and destiny. By studying the CMB, scientists can infer the density of matter and dark matter, the geometry of the universe, and even the nature of dark energy, the mysterious force driving the universe's accelerated expansion. The CMB is also a probe of the universe's earliest moments, offering clues about cosmic inflation and the potential existence of gravitational waves from the Big Bang. In many ways, the CMB is the Rosetta Stone of cosmology, a key to unlocking the universe's deepest secrets. It's a testament to the power of observation and the incredible insights that can be gleaned from the faintest whispers of the cosmos. Quantum fluctuations, seeds of structure. In the beginning, there was a singularity, a point of infinite density and temperature. Then, in a cosmic blink, the Big Bang happened. But the universe didn't just inflate like a balloon. It had a bit of a stutter, a series of quantum hiccups. These tiny fluctuations, smaller than a proton, were the seeds that would eventually grow into galaxies, stars, and planets. Think of them as the universe's first doodles, random squiggles that would later become the grand masterpiece we see today. These quantum fluctuations were tiny variations in the density of the early universe. Some regions were slightly denser than others, like a freshly fallen snow drift with tiny, almost imperceptible, lumps. Over time, gravity took notice. It pulled more matter into these dense regions, making them denser still. This process, called gravitational collapse, is like a snowball rolling down a hill, gathering more snow as it goes. In this case, the snowballs were clouds of gas and dust, and they grew into the large-scale structures we see in the universe today. The fluctuations weren't just random noise. They followed a pattern, a symphony of sorts, written in the language of quantum mechanics. This pattern, imprinted on the cosmic microwave background radiation, is like a baby's first ultrasound, a fuzzy picture that holds clues about the future. Scientists study this pattern to understand the initial conditions of the universe and how it evolved. It's like reading a cosmic recipe book, trying to figure out how to bake a universe. The seeds of structure didn't just grow into galaxies. They also influenced the formation of the cosmic web, a vast network of filaments and voids that make up the large-scale structure of the universe. This web is like a spider's web, with galaxies and clusters of galaxies strung along the filaments and vast, empty voids in between. The quantum fluctuations, those tiny hiccups in the early universe, set the stage for this cosmic ballet, guiding the formation and evolution of the structures we see today. It's a testament to the power of the small, a reminder that the universe's grand design often begins with the tiniest of details. The particle soup, quarks and leptons emerge. In the scorching crucible of the early universe, a mere fraction of a second after the Big Bang, the cosmos was a seething cauldron of energy. This wasn't the kind of energy you'd find in a bustling city or a roaring river, but rather, the raw, untamed energy of fundamental particles, zipping around at velocities that would make a bullet train look like a snail. Picture a cosmic soup, not the kind you'd slurp up on a cold day, but a particle soup, a dense, hot broth where the ingredients were quarks and leptons, the building blocks of matter as we know it. Quarks, those elusive, never-isolated particles, came in a variety of flavors: up, down, charm, strange, top, and bottom. They were the tiny, indivisible seeds from which protons and neutrons would eventually grow. Leptons, on the other hand, were the lightweights of the particle world, with the electron being the most famous family member. In this primordial soup, quarks and leptons were as common as air, bouncing off each other in a chaotic dance, their interactions governed by the fundamental forces of nature. The universe was a symphony of creation and annihilation. Particles popped in and out of existence like bubbles in a champagne glass. Quarks and antiquarks, electrons and positrons, they all danced this high-energy tango. It was a time of perfect symmetry, where matter and antimatter existed in equal measure. Yet, in this seemingly balanced cosmos, a subtle asymmetry lurked, a tiny bias that would eventually tip the scales in favor of matter, allowing the universe, and us, to exist. This particle soup wasn't uniform, though. It had ripples, quantum fluctuations that would later grow into the cosmic structures we see today. These ripples were the seeds of galaxies, the embryonic forms of the grand cosmic web. As the universe expanded and cooled, these fluctuations became more pronounced, setting the stage for the complex structures that would emerge billions of years later. The particle soup was more than just a hot, dense mess. It was the foundation of everything that would come after. Symmetry breaking, the Higgs field awakens. In the grand symphony of the universe's birth, the Higgs field was the silent conductor, waiting for its moment to awaken. Picture a vast, featureless ocean, where every point is identical, every direction the same. This was the universe in its earliest moments, a place of perfect symmetry. Then, as the universe cooled, the Higgs field stirred. It's like watching a frozen lake begin to melt, the ice cracking and shifting, breaking the uniformity of the surface. This is symmetry breaking, a pivotal moment when the universe's fundamental forces began to differentiate, setting the stage for the cosmos we know today. The Higgs field is a bit like an invisible landscape that permeates the entire universe. Every fundamental particle travels through this landscape, but some encounter more resistance than others. It's as if some particles are wading through treacle, while others skate effortlessly on ice. This resistance is what gives particles their mass. The Higgs field doesn't give mass to particles directly. Instead, it's the resistance to their movement through the field that we interpret as mass. It's a subtle but crucial distinction, like the difference between a river's current slowing a boat and the boat itself gaining weight. Consider the humble electron. As it moves through the Higgs field, it's like a dancer moving through a crowded ballroom, constantly bumping into other dancers. These interactions slow the electron down, making it seem as if it has mass. Meanwhile, a photon, or particle of light, glides through the field unimpeded, like a skilled ice skater. This is why light has no mass. It doesn't interact with the Higgs field in the same way. The symmetry breaking of the Higgs field is what allows for this diversity in particle behavior, creating the rich tapestry of matter and energy that makes up our universe. The process of symmetry breaking is akin to a phase transition, like water turning into ice. In the early universe, the Higgs field was in a symmetric state, much like water above freezing. As the universe cooled, the field underwent a phase transition, settling into a lower energy state and breaking the initial symmetry. This transition was not uniform. It happened in different places at different times, creating bubbles of the new phase that expanded and collided. These collisions released energy, much like the popping of bubbles in a glass of champagne. This energy could have been responsible for some of the universe's initial irregularities, seeding the formation of galaxies and other large-scale structures. The first nuclei, protons and neutrons, form. In the cosmic symphony that followed the Big Bang, the universe was a hot, dense soup of quarks, leptons, and their antiparticles. Picture a vast, roiling sea of energy where particles darted about like fireflies in a summer night. As the universe expanded and cooled, the stage was set for the formation of the first nuclei. Protons and neutrons, the building blocks of atomic nuclei, emerged from a process called baryogenesis. This was like a cosmic recipe, where quarks combined under the influence of the strong nuclear force, forming the ingredients for everything that would come later. The dance of protons and neutrons began about 1 second after the Big Bang. At this point, the universe was a hot, dense plasma, a far cry from the cold, empty void we often imagine. Protons, with their positive charge, and neutrons, with no charge, started to form. It was a delicate balance, like a tightrope walker balancing on a thin wire. The ratio of protons to neutrons was determined by the interplay of the weak nuclear force and the cooling universe. As the universe expanded, it cooled, allowing these particles to combine and form the first nuclei. The process was far from straightforward. It was more like a complex game of musical chairs, where particles had to find the right partners to form stable nuclei. The first nuclei to form were those of hydrogen and helium, the lightest and most abundant elements in the universe. Protons, with their positive charge, could combine with electrons to form hydrogen atoms. Neutrons, on the other hand, could combine with protons to form helium nuclei. This was the beginning of nuclear fusion, the process that powers stars and gives life to the universe. The formation of these first nuclei was a crucial step in the evolution of the universe. It was like the first note in a symphony, setting the tone for everything that would follow. These nuclei would later form the building blocks of stars, planets, and even life itself. The process was not instantaneous, but rather a gradual evolution, like a seed growing into a mighty tree. It was a testament to the incredible complexity and beauty of the universe, a cosmic ballet that continues to this day. The Light Element Festival, Big Bang nucleosynthesis. In the Cosmic Symphony, about 3 minutes after the Big Bang's opening note, the universe was a hot, dense soup of particles. Protons and neutrons, the building blocks of atomic nuclei, were swirling around, colliding and combining in a frenzy. This period, known as Big Bang nucleosynthesis, was like a cosmic festival of light elements, where the universe's first atoms were forged. The temperature was a toasty 1 billion degrees Kelvin, perfect for nuclear fusion to occur. It was like a cosmic kitchen, where the universe was cooking up its first ingredients. The main stars of this festival were hydrogen, helium, and a smattering of lithium. Protons, which are just hydrogen nuclei, were the most abundant. They combined with neutrons to form deuterium, a heavy isotope of hydrogen. Deuterium then combined with more protons and neutrons to form helium-3 and helium-4. It was a rapid process, like a cosmic game of atomic Lego, where particles were snapping together to form the simplest of atoms. The universe was a bustling marketplace of particles, trading and combining, creating the first atomic nuclei. However, this festival wasn't a free-for-all. The conditions had to be just right. If the universe was too dense, all the neutrons would have been absorbed into helium-4, leaving no deuterium or helium-3. If it was too sparse, the neutrons would have decayed before they could combine with protons. But the universe was just right, like the Goldilocks of cosmic conditions. The result was a universe with about 75% of hydrogen, 25% of helium, and trace amounts of lithium. It was a cosmic recipe that set the stage for the universe we see today. The Light Element Festival was a brief but crucial period in the universe's history. It lasted only about 17 minutes, but in that time, the universe created the building blocks for the first stars and galaxies. It was like a cosmic seed planting, where the universe was sowing the seeds for its future evolution. The elements created during this time are still with us today, a testament to the universe's early days. They are the cosmic fossils, the remnants of the universe's first festival of light. The universe cools, the era of recombination. The universe, a vast and ever-expanding canvas, was once a hot, dense soup of particles and radiation. As it expanded, it cooled, much like a pot of water taken off the boil. This cooling was not a gentle, linear process, but a rapid, chaotic dance of particles slowing down and combining. About 380 years after the Big Bang, the universe had cooled enough for something extraordinary to happen. Electrons and protons began to combine, forming the first neutral hydrogen atoms. This period, known as the era of recombination, was a pivotal moment in the universe's history. Picture a bustling city at night, its streets filled with people rushing about, colliding and scattering. Now, imagine the city gradually emptying, the streets clearing, and people pairing up, walking off into the night together. This is akin to what happened during recombination. The people in our cosmic city are the electrons and protons, and their pairing up is the formation of neutral hydrogen atoms. As these atoms formed, the universe became more transparent. Before recombination, the universe was opaque, with photons, light particles, constantly scattering off free electrons. But with the formation of neutral atoms, photons could travel freely, setting the stage for the universe we see today. The light released during this time is still visible today, stretched and cooled by the universe's expansion into the cosmic microwave background, CMB, radiation. Think of the CMB as the universe's baby picture, a snapshot of what it looked like in its infancy. This radiation is incredibly uniform, with tiny fluctuations that hint at the seeds of structure formation. These fluctuations are like the subtle ripples on a pond's surface, small disturbances that grow and evolve over time, eventually forming the galaxies and clusters we see today. The era of recombination, then, was not just a cooling-off period, but a crucial step in the universe's journey from a hot, dense state to the complex, structured cosmos we inhabit. The cosmic dark ages, a universe in the fog. Picture the universe as a vast, dark forest, shrouded in a thick fog. This is the cosmic dark ages, a time when the universe was a cold, dark, and foggy place. It began about 380 years after the Big Bang, when the universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms. These atoms absorbed the radiation left over from the Big Bang, scattering it in all directions. This scattering is what we see today as the cosmic microwave background, CMB, radiation, a faint glow that permeates the entire universe. But back then, it was a dense fog that obscured everything. In this foggy universe, gravity was the main player. It pulled together the neutral hydrogen atoms, clumping them into denser and denser regions. These clumps would eventually become the seeds of the first stars and galaxies. But this process was slow, and it took millions of years for the first stars to form. Meanwhile, the universe was a vast, empty space, filled with a fog of hydrogen atoms and bathed in the faint glow of the CMB radiation. The cosmic dark ages were a time of quiet and stillness. There were no stars to light up the sky, no galaxies to form grand spirals and ellipticals. Just a vast, dark expanse, filled with the potential for everything that was to come. It was a universe in the fog, waiting for the first stars to pierce the darkness and illuminate the cosmos. This period lasted for hundreds of millions of years, a vast expanse of time that dwarfs human history. It was a time of slow, inexorable change, as gravity did its work and the first structures began to form. The first stars, lighthouses in the dark. In the vast, dark expanse of the early universe, the first stars ignited like lighthouses piercing through the fog. These celestial beacons, known as population third stars, were colossal, often hundreds of times more massive than our sun. They were the universe's first heavyweight champions, forged from the pristine, metal-free gas that filled the cosmos after the Big Bang. Their brief, brilliant lives were short but impactful, like a firework display that seeds the sky with glittering remnants. Think of these first stars as cosmic alchemists. They were the universe's first factories, fusing the simplest elements, hydrogen and helium, into heavier ones like carbon, oxygen, and iron. When they exploded as supernovae, they scattered these newly minted elements across the cosmos. This stellar recycling was crucial. It enriched the universe with the raw materials needed for everything that followed: planets, life, and even the very ground beneath our feet. The light from these early stars didn't just illuminate the darkness. It also played a crucial role in reionizing the universe. After the Big Bang, the universe was a hot, dense soup of particles. As it expanded and cooled, it became a neutral gas, a foggy mist that blocked light. The intense ultraviolet radiation from the first stars stripped electrons from hydrogen atoms, clearing the fog and making the universe transparent to light. This process, called reionization, was like turning on the lights in a dimly lit room, allowing the universe to become the vibrant, star-studded place we see today. These first stars were also the universe's first architects. Their gravitational pull shaped the large-scale structure of the cosmos. They clustered together, forming the seeds of galaxies. Over time, these clusters grew, pulling in more matter and eventually giving birth to the galaxies we see today. So, in a very real sense, the first stars were the architects of the cosmic web, the grand design that connects everything in the universe. Their legacy is written in the stars, galaxies, and even in us. Galaxy formation, gravity's masterpiece. In the vast cosmic symphony, gravity takes center stage, conducting the formation of galaxies with an invisible baton. It's the silent architect, shaping the universe's grand design. After the cosmic inflation, the universe was a hot, dense soup of particles. As it cooled, gravity began to exert its influence, pulling matter together. This process was slow and steady, like a cosmic dance, with gravity gently tugging at the threads of the universe's fabric. Picture a vast, empty ballroom. Invisible hands reach out, pulling particles together, forming clusters. These clusters grow, attracting more particles, like a snowball rolling down a hill, gathering more snow. Over time, these clusters become dense enough to form the seeds of galaxies. It's a slow process, taking millions of years, but gravity is patient. It's the ultimate matchmaker, bringing particles together in a cosmic dance that will last for eons. Now, imagine these clusters as tiny islands in a vast cosmic sea. Gravity continues to pull matter towards these islands, building them up, making them larger and more massive. As they grow, they start to spin, like a figure skater pulling in their arms. This spin is crucial, as it prevents the galaxy from collapsing in on itself. It's a delicate balance, a cosmic tightrope walk, with gravity as the performer. The result is a beautiful, swirling galaxy, a testament to gravity's masterful work. The large-scale structure, the cosmic web. Picture the universe as a vast, intricate spider web, with galaxies as the glittering dewdrops clinging to its threads. This cosmic web is the large-scale structure of the universe, a mind-boggling network that spans hundreds of millions of light-years. It's not a random mess, though. This web has a pattern, a rhythm, a structure that tells the story of our universe's growth and evolution. The threads are made up of dark matter, an invisible cosmic glue that pulls galaxies together. The dewdrops are the galaxies themselves, shining brightly against the dark backdrop of space. This structure is the result of tiny quantum fluctuations in the early universe, magnified over billions of years by gravity. Think of it like a city's road network. Some roads are like the dense clusters of galaxies, bustling with activity. Others are like the vast cosmic voids, empty and quiet. The highways connecting these clusters are the filaments of dark matter, guiding galaxies along their cosmic journeys. The largest structures in the cosmic web are the superclusters, massive agglomerations of galaxies that stretch across hundreds of millions of light-years. They're like the sprawling metropolises of the universe, teeming with life and activity. Yet, even these giants are not evenly distributed. They're part of an even larger pattern, a tapestry woven by the invisible hand of dark matter and the relentless pull of gravity. The cosmic web is not static. It's dynamic, evolving, changing. Galaxies move along the filaments, drawn towards the dense clusters. They collide, merge, grow. New stars are born, old ones die. The web itself is stretching, expanding, as the universe grows. This expansion is accelerating, driven by a mysterious force called dark energy. It's like the city's roads are constantly being repaved, expanded, redirected. The cosmic web is a living, breathing entity, a testament to the dynamic nature of our universe. It's a structure that's both beautiful and brutal, a dance of creation and destruction that has been playing out for billions of years. Dark matter, the invisible scaffolding. Dark matter is the cosmic glue that holds galaxies together, yet it's invisible, detectable only by its gravitational effects. Think of it as the unseen scaffolding of the universe, the unseen framework that gives shape and structure to the cosmos. It's like the dark stagehands of a grand theater, unseen but essential for the performance. Without dark matter, galaxies would fly apart, their stars scattering like marbles on a floor. It's estimated to make up about 27% of the universe's total mass and energy content, far outweighing the ordinary matter that makes up stars, planets, and all visible structures. The nature of dark matter remains one of the most profound mysteries in cosmology. It doesn't emit, absorb, or reflect light, making it invisible to telescopes. Scientists infer its presence through its gravitational influence on visible matter, like observing the ripples on a pond to understand the stone that created them. One of the most compelling pieces of evidence comes from the rotation curves of galaxies. Stars on the outskirts of galaxies move at similar speeds to those near the center, defying the expected drop in velocity based on visible matter alone. This suggests an invisible mass, dark matter, exerting a gravitational pull. Dark matter's role becomes even more crucial when we look at the large-scale structure of the universe. It acts as a gravitational seed, pulling in ordinary matter and facilitating the formation of galaxies and galaxy clusters. Without dark matter, the universe would be a much lonelier place, with fewer galaxies and less structure. Yet, despite its importance, its composition remains unknown. Candidates range from weakly interacting massive particles, WIMPs, to primordial black holes, but none have been definitively detected. The search for dark matter is ongoing, with experiments deep underground and in space hoping to catch a glimpse of this elusive cosmic scaffolding. Dark energy, the mysterious accelerator. In the vast cosmic ballet, dark energy is the enigmatic dancer that's been pushing the universe's expansion into overdrive. Picture it like an invisible hand, gently but persistently pressing the gas pedal of the cosmos. This mysterious force makes up about 68% of the universe's energy density, yet its nature remains as elusive as a shadow in the dark. Scientists have a few ideas about what it could be, but none have been confirmed yet. One leading theory is that it's a property of space itself, a kind of energy associated with the vacuum of space, which would explain why it's so evenly distributed throughout the universe. Think of dark energy as the universe's built-in stretching mechanism. It's like a rubber band that keeps getting longer, but instead of snapping back, it just keeps stretching, pulling galaxies farther and farther apart. This acceleration was first observed in the late 1990s when astronomers studied distant supernovae and found that they were dimmer than expected, indicating that the universe's expansion was speeding up. It's as if the universe has been given a cosmic energy drink, and it's wide awake and expanding faster than ever. The discovery of dark energy has turned our understanding of the universe on its head. It's like finding out that the ground you're standing on is actually a trampoline, and it's bouncing you higher and higher with each step. This acceleration is causing galaxies to move away from each other at an ever-increasing rate, a phenomenon that's been dubbed the cosmic acceleration. It's a bit like a game of musical chairs, but instead of chairs, it's galaxies, and the music never stops. The implications of this are profound, as it suggests that the universe may end, not with a bang, but with a whimper, as galaxies become so far apart that they can no longer interact or even see each other. The accelerating universe, a cosmic surprise. In the grand symphony of the cosmos, astronomers once believed the universe was like a ball thrown into the air, slowing down under the relentless pull of gravity. But in the late 20th century, they discovered something astonishing. The universe isn't slowing down, it's speeding up. This cosmic surprise, driven by an enigmatic force called dark energy, has turned our understanding of the universe on its head. Picture the universe as a vast, ever-expanding balloon. For years, scientists thought the dots on this balloon, galaxies, would move slower and slower as the balloon expanded due to the gravitational pull between them. But in 1998, observations of distant supernovae revealed that the expansion is not decelerating but accelerating. It's as if the balloon is being inflated at an ever-increasing rate, with no clear end in sight. This acceleration is attributed to dark energy, a mysterious force that makes up about 68% of the universe's total energy density. Yet, despite its prevalence, we know very little about it. It's like trying to understand a symphony by only hearing the bass line. The discovery of the accelerating universe has profound implications. It suggests that the fate of the universe might be a cold, dark, and lonely place. As galaxies speed away from each other, they'll become so distant that they'll be unable to interact or even see each other. This concept, known as the Big Freeze or heat death, paints a bleak picture of the universe's ultimate fate. Yet, it's also a reminder of how much we still don't know. Dark energy remains one of the biggest mysteries in physics, a cosmic enigma that challenges our understanding of the universe and our place within it. It's a humbling thought, a stark reminder that the universe is under no obligation to make sense to us. The fate of the universe, heat death or big crunch. The universe, in its grand cosmic ballet, is a dance of expansion and cooling. Like a balloon being inflated, it stretches outward, and as it does, the temperature of the cosmos drops. This is the scenario painted by the theory of the Big Bang, where everything began from a singularity, a point of infinite density and temperature. The universe has been expanding and cooling ever since, and this process raises intriguing questions about its ultimate fate. Two primary theories vie for attention: the heat death and the big crunch. Heat death, a chilling prospect, suggests that the universe will expand forever, growing colder and darker. Think of it as a cosmic winter, where all stars burn out and galaxies drift apart into the void. Entropy, the measure of disorder, will reach its maximum, and no energy will be available to sustain life or any meaningful processes. It's like a grand cosmic battery running out of juice, leaving everything in a state of eternal slumber. This scenario is supported by observations of the universe's accelerating expansion, driven by the mysterious dark energy. On the other hand, the Big Crunch offers a more dramatic ending. In this scenario, the expansion of the universe slows down, halts, and then reverses. Gravity takes over, pulling everything back together in a cosmic implosion. The universe collapses in on itself, potentially leading to a new Big Bang and a cyclical pattern of creation and destruction. This idea is akin to a cosmic breath, inhaling and exhaling over eons. However, current observations suggest that dark energy is overcoming gravity, making the Big Crunch less likely, but not entirely impossible. The fate of the universe is a complex puzzle, with pieces still being discovered. Scientists are actively studying dark energy, the acceleration of the universe's expansion, and the nature of gravity to piece together this cosmic mystery. The answers they find will shape our understanding of the ultimate destiny of the cosmos. Until then, the dance continues, and the universe keeps expanding, cooling, and evolving in ways that challenge our imagination and push the boundaries of our knowledge. The multiverse hypothesis: are we alone? The cosmos is a vast, sprawling tapestry, and our universe is but a single thread within it. The multiverse hypothesis suggests that our universe is one among countless others, each with its own fields and interactions. Think of it like a colossal foam, where each bubble is a universe, and the spaces between them are filled with something entirely different. This idea isn't just science fiction. It's a serious consideration in modern cosmology, stemming from theories like eternal inflation and string theory landscape. In eternal inflation, our universe is a pocket where inflation has ended, allowing matter and energy to form. Other universes could still be inflating, creating a vast multiverse. Meanwhile, string theory landscape proposes that there are many possible universes, each with different physical constants and dimensions. Now let's talk about the elephant in the room. Are we alone? In our universe, we've yet to find definitive signs of life beyond Earth. But if the multiverse exists, the possibilities expand exponentially. Some universes might be barren, while others could be teeming with life, perhaps even life forms we can't begin to comprehend. It's like searching for a specific grain of sand on a single beach versus searching across every beach on Earth. The multiverse could be a cosmic game of hide and seek, with life hiding in plain sight, just beyond our current reach. But how can we explore this idea? Direct observation is currently impossible, as other universes could be beyond our observable horizon or even in higher dimensions. However, scientists are exploring indirect methods. Some propose looking for anomalies in the cosmic microwave background radiation, the afterglow of the Big Bang. Others suggest that collisions between universes could leave detectable traces. It's like trying to find footprints in the snow, but the snow is the fabric of space-time itself. Until we find concrete evidence, the multiverse remains a tantalizing possibility, a cosmic what-if that fuels both scientific inquiry and imagination. The Big Bang's critics, alternative theories. The Big Bang Theory, with its grand narrative of a universe bursting from a singularity, has long been the cornerstone of cosmology. Yet, it's not without its critics. Some scientists argue that the theory has gaps, like a symphony missing a few notes. These critics propose alternative theories, each with its own unique melody. One such theory is the steady-state model, which suggests the universe has always existed in the same state, with matter continuously created to maintain a constant density. It's like a cosmic juggler, constantly adding new balls to keep the performance going. However, this theory has largely fallen out of favor, as it struggles to explain the cosmic microwave background radiation, the afterglow of the Big Bang. Another alternative is the Big Bounce theory. Picture a cosmic yo-yo, where the universe expands and then contracts, only to bounce back and expand again. This theory suggests that our universe might have been preceded by a previous universe that collapsed in a big crunch, setting the stage for our current expansion. It's an elegant idea, but it's not without its challenges. The theory requires a detailed understanding of quantum gravity, which we're still far from achieving. Moreover, it's not clear if a bounce is even possible, or if the collapse would lead to a singularity instead. Then there's the multiverse theory, a cosmic archipelago where our universe is just one island among many. In this scenario, the Big Bang might not have been a singular event, but one of many. Each universe could have its own set of physical laws and constants. It's a mind-bending idea, but it's gained traction in recent years. Some scientists argue that the multiverse could explain the fine-tuning of our universe, making it seem like a cosmic lottery where we just happened to win the jackpot. However, the multiverse is also highly speculative, and there's currently no way to test it. It's like trying to navigate a map with most of the territory blank. Lastly, there's the conformal cyclic cosmology theory, proposed by Sir Roger Penrose. Imagine a cosmic phoenix, where the universe is reborn from its own ashes. In this theory, the universe goes through endless cycles of expansion and contraction, but the singularity at the end of each cycle is avoided. Instead, the universe transitions smoothly into a new expansion phase. It's a radical idea, but it's gained some attention for its unique approach to the singularity problem. However, like the other alternatives, it's not without its challenges. The theory requires a radical rethinking of our understanding of time and gravity. The Big Bang's evidence, what we've found so far. The universe, in its grandest spectacle, began with a whisper, a cosmic hush that exploded into a symphony of creation. This whisper, the Big Bang, left behind echoes, traces, and fingerprints that scientists have been deciphering for decades. The most compelling evidence comes from the cosmic microwave background, CMB, radiation, a faint glow that permeates the entire universe. Think of it as the universe's baby picture, a snapshot of the cosmos when it was just 380 years old. This radiation, discovered accidentally in 1965, matches predictions made by the Big Bang Theory, providing strong support for the idea that the universe began in a hot, dense state. Another piece of the puzzle is the abundance of light elements like hydrogen, helium, and lithium. The Big Bang nucleosynthesis, the process that occurred within the first 3 minutes of the universe's existence, predicted the exact amounts of these elements. Observations of these elements in the universe match these predictions remarkably well. It's like finding a recipe that perfectly matches a delicious dish, confirming that the ingredients and the cooking process were just right. This concordance gives scientists confidence that the Big Bang Theory is on the right track. The distribution of galaxies and galaxy clusters also tells a story that aligns with the Big Bang Theory. The universe is not uniform. It has a web-like structure with vast voids and dense clusters of galaxies. This structure formed over billions of years, starting from tiny quantum fluctuations that were stretched to cosmic sizes during a period of rapid expansion known as cosmic inflation. It's like a cosmic game of connect the dots, where the dots are galaxies, and the lines are the gravitational forces that pulled them together. The pattern we see today is consistent with what the Big Bang Theory predicts, providing yet another piece of evidence for this leading cosmological model. Lastly, the redshift of distant galaxies, a phenomenon where the light from these galaxies is shifted towards the red end of the spectrum, indicates that the universe is expanding. This expansion is a direct consequence of the Big Bang. The farther away a galaxy is, the faster it's moving away from us, a relationship known as Hubble's law. It's like being in a cosmic traffic jam, where the farther away a car is, the faster it's moving away from you. This observation not only supports the Big Bang Theory, but also provides a way to measure the age and size of the universe. The Big Bang's mysteries, what we still don't know. The universe, in its vast and mind-boggling expanse, is like an intricate puzzle with pieces still missing. The Big Bang, the cosmic event that set everything into motion, is one of the most well-supported theories in science. Yet, it's far from being fully understood. Think of it as a grand symphony where we can hear the melody and some of the instruments. But there are still sections that are muffled or missing entirely. One of the biggest mysteries is what exactly happened at the very beginning, at the Singularity. This isn't just a scientific question, it's a philosophical one too. The Singularity is like the eye of a hurricane, a point where the laws of physics as we know them break down. We don't know if time and space even existed before the Big Bang, or if they came into being at that moment. It's like trying to describe the color blue to someone who has been blind from birth. Our current tools and theories, like the theory of general relativity and quantum mechanics, can't bridge this gap. They're like two people speaking different languages, trying to have a conversation. Another head-scratcher is the nature of cosmic inflation, the rapid expansion of the universe just after the Big Bang. It's like a balloon being inflated at an incredible speed, but we're not sure what caused it or what drove it. The leading theory involves a hypothetical field called the inflaton, but we haven't found any direct evidence of it yet. Moreover, the universe seems to be fine-tuned for life, with just the right amount of density and expansion. This is often referred to as the fine-tuning problem, and it's a topic of hot debate among scientists and philosophers alike. Is it a coincidence, or is there something deeper going on? The jury is still out on that one. Then there's the matter of dark matter and dark energy, which make up about 95% of the universe. We can see their effects, but we can't observe them directly. It's like trying to understand a party when you can only hear the music and feel the vibrations, but you can't see the people or the room. Dark matter is like an invisible glue that holds galaxies together, while dark energy is like a mysterious force that's pushing the universe apart. We're still in the dark about what they're made of and how they work. The more we learn, the more we realize how much we don't know. It's a humbling thought, but it's also what makes science so exciting. The universe is full of surprises, and each new discovery opens up 100 new questions. The Big Bang's legacy, our place in the cosmos. The universe, in its grandest sense, is a cosmic symphony, a vast expanse of time and space that has been playing out since the very beginning. The Big Bang, often likened to the cosmic equivalent of a spark, set the stage for everything that followed. It's not so much an explosion in the traditional sense, but rather a rapid expansion from an incredibly hot, dense state. Think of it as a cosmic balloon being inflated, with galaxies, stars, and planets stretching out like tiny specks of paint on its surface. This initial burst of expansion, known as cosmic inflation, laid the groundwork for the universe as we know it today. In the grand tapestry of the cosmos, we are but tiny threads, woven into the fabric of existence. Our place in the universe is a humbling one, a testament to the sheer scale and complexity of the cosmos. The atoms that make up our bodies, the air we breathe, and the world we inhabit were all forged in the fiery furnaces of stars, billions of years ago. We are, quite literally, stardust, a reminder of our deep connection to the universe and its ongoing evolution. This cosmic legacy is a profound one, a reminder of our place in the grand scheme of things. The legacy of the Big Bang is not just a story of the past, but a continuing narrative that shapes our present and future. It's a reminder that we are part of something much larger than ourselves, a cosmic dance that has been playing out for billions of years. From the tiniest subatomic particles to the largest galaxy clusters, everything is interconnected, a testament to the unity and diversity of the cosmos. Our understanding of the Big Bang and its aftermath has given us a new perspective on our place in the universe, a sense of awe and wonder that transcends the boundaries of time and space. It's a legacy that continues to inspire and challenge us, a reminder of the endless possibilities that lie ahead. The Big Bang's future. What's next in cosmology? The universe, in its current state, is a vast, ever-expanding tapestry of galaxies, stars, and cosmic dust. It's like a giant, intricate puzzle, and scientists are constantly trying to piece together its origins and ultimate fate. The Big Bang Theory is our best attempt to understand this cosmic puzzle, but it's far from complete. So what's next in cosmology? Let's dive in. Picture the universe as a loaf of bread baking in an oven. At first, it's a single, dense, hot mass. As it cools and expands, bubbles form, creating the structure we see today. This is similar to cosmic inflation, a period of rapid expansion that occurred just after the Big Bang. But what drove this inflation? What was the universe like before it? These are some of the burning questions cosmologists are trying to answer. They're like detectives, searching for clues in the cosmic microwave background radiation, the afterglow of the Big Bang. Each clue brings us one step closer to understanding the universe's earliest moments. Now, let's talk about dark energy. It's a mysterious force that's causing the universe's expansion to accelerate. Think of it as an invisible hand, pushing the galaxies apart. But what is it? Where does it come from? These are some of the biggest mysteries in cosmology. Scientists are using powerful telescopes and particle accelerators to study dark energy, hoping to unravel its secrets. They're like explorers, venturing into uncharted territory. Each discovery brings us one step closer to understanding the universe's ultimate fate. But the universe is a vast and complex place, and there's still so much we don't know. For instance, what happened before the Big Bang? Was there a previous universe? Or was the Big Bang truly the beginning? These are some of the most profound questions in cosmology. They're like riddles, waiting to be solved. And as our technology advances, we're getting closer to finding the answers. The future of cosmology is bright, and it's an exciting time to be a part of it. So, buckle up and enjoy the ride. The universe is waiting to be discovered. The Big Bang's cultural impact, from science to pop culture. The Big Bang Theory, once a niche scientific concept, has exploded into the mainstream, reshaping our cultural landscape like a cosmic supernova. It's not just about the science anymore. It's a metaphor for beginnings, a symbol of the vast and mysterious universe we inhabit. Think of it as the ultimate origin story, a cosmic once upon a time that has captured the imagination of scientists and storytellers alike. From documentaries to sitcoms, from serious dramas to playful cartoons, the Big Bang has left its fingerprints all over pop culture. Take, for instance, the popular TV show The Big Bang Theory. While it's a comedy, it's also a testament to the theory's cultural permeation. The show's characters, all scientists, often reference the Big Bang, cosmic inflation, and other complex concepts, making them accessible and entertaining to a wide audience. It's like taking a complex scientific recipe and turning it into a delicious, easy-to-swallow cultural dish. The show's success is a clear indication that people are not only interested in the Big Bang, but also eager to engage with it in a fun, lighthearted way. Moreover, the Big Bang has inspired countless works of art, literature, and music. It's a recurring theme in science fiction, often serving as a backdrop for epic tales of creation, destruction, and rebirth. In music, it's been used as a metaphor for love, life, and even political movements. Artists have painted it, poets have written about it, and filmmakers have depicted it in stunning visual spectacles. It's as if the Big Bang has become a universal language, a shared cultural shorthand that transcends borders and disciplines. This cultural impact is a testament to the theory's power to inspire, to provoke thought, and to spark the imagination. It's not just a scientific theory, it's a cultural phenomenon. The Big Bang's philosophical implications. What does it mean? The universe, in all its vast and wondrous expanse, began as a singularity, a point of infinite density and temperature. This singularity, like a cosmic seed, contained all the matter and energy that would eventually become everything we see today. It's a mind-bending concept, like trying to imagine the entire ocean squeezed into a single droplet. The Big Bang, the rapid expansion of this singularity, didn't happen at a specific point in space. Rather, it was the sudden stretching of space itself, like the surface of a balloon being inflated, with every point moving away from every other point. This cosmic inflation, a period of exponential growth, is like the universe's first breath, a rapid expansion that set the stage for the formation of galaxies, stars, and planets. It's a process that's still ongoing, with the universe continuing to expand and evolve. But here's where things get really interesting. The Big Bang isn't just a scientific theory, it's a philosophical game-changer. It challenges our understanding of time, space, and existence itself. If the universe began as a singularity, what came before it? This is a question that has puzzled scientists and philosophers alike, like a riddle wrapped in an enigma. The Big Bang suggests that time itself began with the universe. Before the singularity, there was no before. It's a concept that's difficult to grasp, like trying to imagine the edge of the universe or the sound of silence. This challenges our linear understanding of time, suggesting instead a cyclical or perhaps even a timeless existence. It's a humbling thought, a reminder of our place in the grand scheme of things. We're not the center of the universe, but rather a tiny part of a vast and complex whole. Moreover, the Big Bang raises questions about the nature of existence. If the universe came from nothing, what does that say about the nature of reality? It's a question that delves into the heart of philosophy, challenging our understanding of being and non-being. It's like standing at the edge of a cliff, looking out into the void and wondering what lies beyond. The Big Bang, in its simplicity and complexity, is a reminder of the mysteries that still lie unsolved, a testament to the enduring quest for knowledge and understanding. It's not just a theory about the origin of the universe. It's a philosophical journey, a journey that invites us to question, to explore, and to wonder. All right, let's wrap this cosmic journey up. So, we've zoomed from a teeny-tiny singularity to a universe blowing up like a balloon on steroids. Imagine the Big Bang as the ultimate cosmic pop, and inflation? That's the universe hitting the fast-forward button, stretching out faster than a rubber band pulled by a couple of hyperactive kids. We've got matter dancing to the tune of gravity, and energy playing tag with the other forces. It's like the universe's own game of cosmic chaos tag, and we're all just trying to keep up. Now, you might be thinking, that's all well and good, but what's next? Well, buckle up, because we're just getting started. Next time, we're diving into the cosmic microwave background, the universe's baby picture. It's like looking at an old Polaroid of the cosmos, and it's gonna blow your mind. But for now, hit that like button if you're ready to explore the universe with us. And don't forget to subscribe, because we're just getting warmed up. The cosmos is calling, and we're here to answer. See you in the next video, Space Cadets.